This is a continuation of the related rates video. We are now on example number 3. Water is flowing at the rate of 2 cubic meters per minute into a tank in the form of an inverted cone, having an altitude of 16 meters and a radius of 4 meters. How fast is the water level rising when the water is 5 meters deep? Let us draw the figure of the problem. Okay, there you have the tank in the form of an inverted cone, and then its base radius is 4 meters here, and then its altitude is 16 meters. All right, so water is flowing at the rate of 2 cubic meters per minute into the tank. All right, so let's answer the problem. All right, just to remind us of the steps in answering the problem. Step 1 is defining the variables starting from time t. Okay, let t be the time elapsed since the water started flowing into the tank in minutes. Okay, so the unit of measure of time here is minutes. What else is changing as time t changes? All right, so as water flows into the tank, the height of the water changes. Or shall we call it depth of the water? All right, we can use the variable h here, or whatever variable that you like. You can use h. Let h be the depth of the water in the tank in meters, okay, in t minutes. What else changes? Because the water is liquid, it follows the form of the tank, okay? So as the water rises, its base radius also changes, right? So this has a base radius r. So it changes as the water level rises, right? So that's another variable r that we need to define. Right? Let r be the radius of the surface of the water in the tank. In meters also, we have to be consistent again, in t minutes. And of course, as the water level rises, the volume of the water in the tank also changes. So let's just use capital V for volume. So let V be the volume of the water in the tank, that is in cubic meters, so in t minutes. Alright, so we're done with step 1. Now let's go to step 2. Step 2. Write down numerical facts about the variables. Numerical facts. 2 cubic meters per minute. 2 cubic meters per minute. Obviously, that's volume change, okay? Change in volume. So 2 cubic meters per minute. So that will be dV over dt, as we have defined V to be the volume of the water in the tank. That's 2 cubic meters per minute. Okay, water is flowing at the rate of 2 cubic meters per minute into the tank. And then 16 meters and the radius of 4 meters are constants. The figure is already labeled. Okay, how fast is the water level rising? Okay, that's for step 3 already. Let's go to step 3. Write down what you wish to find. How fast is the water level rising when the water is 5 meters deep? Water level, okay. So the depth of the water is represented by h. So we are looking for dH over dt. How fast is h changing per unit time? So what is dH over dt when the water is 5 meters deep? 5 meters deep. So when h, the depth of the water is 5 meters. Okay, that's what we're looking for. Alright, now let's go to step 4. So we are to relate 3 variables this time, V, H, and R. Because the tank is in the form of a cone, an inverted cone, so we'll be using the formula in finding the volume of a cone. And that is written as V equals 1/3 times the base of the cone times its altitude h. I'll just use capital H for the altitude, right? Capital H because I have defined small h to be the depth of the water. Capital H for the altitude. Okay, so V is equal to 1/3. Now the base is circular, so the area of the base can be found by using the formula pi r squared, right? Pi r squared. Okay. Times the altitude h. Now maybe I can just use small h here because, yeah, I'm sorry. Okay, so it's 1/3 base times height, or base times the altitude, where h here is defined as the depth of the water. So we are actually pertaining, okay, this formula is pertaining to the volume of the water, not the volume of the tank. Okay, so volume of the water inside the container, inside the tank. So the altitude h is pertaining to the depth of the water. So it's 1/3 pi r squared times h because the base is circular, and the area of a circle can be found using the formula area equals pi r squared. So therefore v is equal to 1/3 pi r squared times h. Okay. Now we can go straight away to step 5. Okay, in step 5 we differentiate both sides with respect to t. But take note that the right side, look at the right side of our equation, involves two variables r and h. Now, if we differentiate the right side will involve the product rule. And by the product rule, you'll have here the derivative of r with respect to t, derivative of r with respect to t because the right side involves the variable r, and you'll also have the derivative of h with respect to t. Okay, now we are looking for dH over dt. Okay, so it's okay to have a dH over dt on the right-hand side of the equation. But if we'll have dr over dt on the right-hand side of the equation, then that's going to be a problem for us. Because we are only given, in step 2, dv over dt. We don't have dr over dt. So it means to say that we have to write our equation in step 4 in terms of v and h only. So we have to find a relationship between r and h so that dr over dt will not be a problem in step 5 after differentiation with respect to t. Okay? Now let's find a relationship between r and h using the figure. Alright, we can find two similar figures here. To be more specific, two similar triangles. This is the larger one. Okay. Now this is the base of the triangle. It measures 4 meters. The altitude of the triangle is equal to the altitude of the tank, so it's equal to 16 meters. Now there's a smaller triangle over here. Okay, let me use another color for that. Let's use blue. Okay, this is the smaller triangle, similar to the bigger one. Okay, now its base is equal to r. Remember that r is defined. It is the radius of the surface of the water, so it's r. And then the altitude of the smaller triangle is h, because we have defined h to be the depth of the water in the tank in d minutes. Okay, so h and r changes as t changes here. H and R change as t changes, alright? Now, just like what we used in number 2, ratio in proportion, okay? Ratio in proportion, we'll be using the ratio of the altitude and base of the two triangles here. Okay, altitude base or base altitude, it doesn't matter. So let's start with the pink triangle, the bigger one. The ratio of the base and the altitude of the bigger triangle, so its base is 4. its altitude is 16. Okay, I will equate that to the ratio of the base to the altitude of the smaller triangle. Right? So blue is, it's R. It's not a good color, so I'll use lighter blue. It's R over H. Okay. So we now have an equation that involves R and H only. So this is the relationship between the two variables, right? So we can, from this equation, from this proportion, we can write one of the variables in terms of the other. So our problem in step 4 is R, because we do not have dr over dt given in the problem. So we want to eliminate R in the equation. Okay, so we'll have to write R in terms of H here by cross multiplication. So I'll just multiply 4 and H. 4 and H, and we'll have 4H over 16 equals R, or that is H over 4 when simplified, right? H over 4 equals R. So we can substitute H over 4 for R in our equation. So V is equal to 1/3, let's go back to step 4, of pi. R is H over 4 squared times H. Simplifying this, we'll have 1/3 of pi. Squaring H and 4, you'll have H squared times H, that's H cubed, over 4 squared, 16. Now I'll just multiply our constants. 1/3 and 1 over 16 will give us 1 over 48 pi. Okay, H cubed. Now this is our equation in terms of V and H only. Okay, now we're ready for step 5. In step 5, we'll just differentiate both sides of the equation with respect to time t. Okay, so the left side will give us dv over dt when you differentiate v with respect to t. Okay, it's denoted by dv over dt. On the right side, we have a constant 1 over 48 pi. So I'll just copy the constant and then differentiate h cubed with respect to t. And that will give us, using power rule, 3h squared times dh over dt. dh over dt is the derivative of the base of the power of h cubed. Okay? So we'll simplify this. We'll have dv over dt equals, well, we have here 3 divided by 48. Okay, 3 divided by 48 is 1 over 16 when simplified. So that is 1 over 16 pi h squared times dh over dt. Okay, now we're ready for step 6. Substitute known values. So dv over dt is given, it's equal to 2. Just don't mind the unit of measure. Okay, in the end, we'll just write them. Equals 1 over 16 pi. H is given, so we want, in step 3, we want dh over dt when h is 5. So 5 squared, and the unknown is dh over dt. Okay, just isolate dh over dt on the right side, right-hand side of the equation, and we'll have our final answer. Alright, so that's 2 on the left side. And then 5 squared is 25, so we have a constant 25 over 16 pi times dh over dt. Okay, so to isolate the dh over dt on the right side, just multiply both sides of the equation by 16 over 25 pi. 16 over 25 pi. So that we'll be able to cancel this. 16 divided by 16 is 1. 25 divided by 25 is 1. Pi over pi is 1. Okay, so from there, we'll have our answer. That's dh over dt equals 16 times 2 is 32 over 25 pi. We can't do anything about our values anymore because it's already simplified. So the unit of measure, this is in meters per minute. Right, minute. So this is the change in the depth of the water as it flows into the tank at the rate of 2 cubic meters per minute. Okay, 32 over 25 pi meters per minute. That's our final answer for number 3. Now on to the last problem. Two cars, one going due east and at the rate of 90 kilometers per hour and the other going due south at the rate of 60 kilometers per hour are traveling toward the intersection of two roads. At what rate are the cars approaching each other at the instant when the first car is 0.2 kilometers and the second car is 0.15 kilometers from the intersection? Let's draw the figure of the problem. Alright, here's the figure. Let me also define our variables starting from time t. Alright, we have three variables. T is the time elapsed since the two cars start to approach each other in hours. So T is in hours here. X is the distance of the blue car, okay, the first car to the intersection in kilometers in T hours. So Y is the distance of the white car, okay, to the intersection in kilometers also in T hours. There are no other variables involved here aside from these three. Okay, let's go to step 2. In step 2, what is given? You're given 60 kilometers per hour in the problem. Okay, so, and also 90 kilometers per hour. Okay, so the one going due east is the first car, so that's the blue car. Okay, its distance from the to the intersection is in terms of x. Okay, is represented by x, so that's dx over dt is equal to 90 kilometers per hour. The other going due south, the white car, at the rate of 60 kilometers per hour, so that's dy over dt, 60 kilometers per hour. Okay. Sorry, there's another variable here because of the question. At what rate are the cars approaching each other at the instant? Okay, so let's define another variable. Another variable would be the distance between the two cars at an instant, right? So it changes as they approach the intersection. Well, I'll be using the variable z. This is z, the distance between the two. So in the figure, this is z, all right? Okay, so z is the distance between the two cars in kilometers also in t hours. And then I've rewritten dx over dt and then dy over dt. So the question is, at what rate are the cars approaching each other at the instant when the first car is, that is the blue car, 0.2 kilometers and the second car is 0.15 kilometers from the intersection. So let's go to step 3. So we want to know what dz over dt is. This is the rate of change. Okay, the rate that the cars are approaching each other because the distance between the two cars is denoted by z. So the rate of the rate where they are the rate that they are approaching each other is denoted by dz over dt. Okay. Now to relate the three variables that we have x, y, and z, we can create the right triangle in our figure. Okay, where this is x, distance of the blue car to the intersection, this is y, and then this is z. Alright, so using the Pythagorean theorem, because we have a right triangle in our figure, so the Pythagorean theorem for that particular triangle is x squared plus y squared is equal to z squared. So we have the relationship among our three variables. We're ready for step 5. Differentiate both sides of the equation with respect to t. Okay, so we'll have the derivative of x squared with respect to t using power rule is 2x times dx over dt, derivative of the base, plus the derivative of y squared with respect to t, that's 2y times dy over dt, equals the derivative of z squared, that is 2z times dz over dt. Okay, dividing both sides of the equation by 2, we'll have it as x dx over dt plus y dy over dt equals z dz over dt. Now we are solving for dz over dt. You are given dx over dt and dy over dt. And you are also given the values of x and y, but you are not given the value of z. Okay? But it's very easy to solve for z given the Pythagorean theorem in step 4. Okay, so in step 4, we can write z if we get the square root of both sides of the equation. So z is the square root of x squared plus y squared. Now remember, we want dz over dt whenever x is 0.2 and y is 0.5. Okay, so we can just substitute 0.2 for x and then 0.15, I mean, for y. 0.15 for y to get the value of z. Okay, so z when x is equal to 0.2 and y is 0.15, sorry, that's 0.15, is square root of, so 0.2 squared plus 0.15 squared. Let's get the value of z. If you'll solve for that, you'll get z equals 0.25. Okay, so now you can substitute all of these values in step 6 to find dz over dt. Let's go to step 6. So in this equation, we'll substitute all the given values. We have x, 0.2, and then dx over dt. That's 90. Okay, plus y. That's 0.15 times dy over dt. That's 60 equals z. We have solved for z, that's 0.25, and then the unknown dz over dt. Just solving for the left side, 0.2 times 90 is 18 when you solve. Plus 0.15 times 60 is 9. Equals 0.25 times dz over dt. Alright, so 18 plus 9 is 27. Equals 0.25 dz over dt. 0.25 is 1/4. Sorry, that's 27. Okay, 0.25 is 1/4. Alright, so this is dz over dt. Okay, so to solve for dz over dt, just multiply both sides of the equation by 4. And we'll get 108 when we multiply 27 by 4. Okay, equals dz over dt. So we have to write our answer with units. So dz over dt is equal to 108. This is in kilometers per hour. Okay, so this is the rate at which the two cars are approaching each other. Okay. So that's it. This is our last example and our last video. Thank you.